Good morning, everyone. Thank you so much for joining us. So today it's my great pleasure to introduce Elena Voita. Elena is a PhD student at the University of Edinburgh and the University of Amsterdam, supervised by Ivan Titov and Rico Stenrich, and is currently a Facebook PhD fellow. Her research focuses on document-level neural machine translation, as well as on understanding what and how neural models learn. Previously, she was a research scientist at the Yandex Research and worked closely with the Yandex Translate team. She also teaches NLP at the Yandex School of Data Analysis. The extended public version of a part of her course is available at the NLP course for you, available through her homepage. I'm also very grateful to Lena. She agreed to this talk given our time difference with Europe. And please join me in welcoming her and enjoying her talk.
Thank you for such a nice introduction. I'm really glad to be here. And I'm really glad it's not too late in Edinburgh. Today I'm going to talk about our paper with my research father, Ivan Titov. It's MNLP paper called Information-Theoretic Probing with minimum description length. So a bit of recap of what's going on in NLP. Probably you noticed that pre-trained models now have huge impact and are extremely popular, but also analysis becomes vital in NLP. And the combination of these two is a very important research area. Most of analysis in NLP tries to understand if a model captures a linguistic property. So usually you have a pre-trained model, for example, Elmer, Bird, or basically whatever you want. You have data, you feed it to a model, and you get vector representations for your data. You can get vector representations from some layer or a combination of these layers. It doesn't matter. What matters is that you have a pre-trained model, and you can get vector representations for your data. And also you have some kind of linguistic labels, for example, part of speech tags. And the task is to understand whether these representations encode labels. Ideally, we would like to measure the relationships between these two. And ideally, we would like to say something like, this layer or model encodes these labels better than that layer or model. For example, Elmer encodes part of speech tags better than Bert, for example. And so what is going to happen? First, I will remind you of the most popular approach of doing this, probing classifiers. Then I'll mention some sanity checks done in previous work. The sanity checks highlight some of the problems of the standard probing. Then I'll come to their information-theoretic point of view on this task, our point of view, and finally we'll look at some experiments. If you have any questions on the way, you're welcome to answer. You're welcome to ask them, and I hope I'll be able to answer. So let's start. The most popular approach, so again, what is our question here? So what can we put between representations and labels to be able to measure the relationships between these two, between x's and y's? And the most popular approach, I'm sure you know about it, the most popular approach is to put here a probing classifier. So this is a classifier which is trained to predict labels from representations. And usually accuracy of a classifier is used as a measure of how well the representations encode labels. So once more, we put here a probing classifier. Goal of this classifier is to predict labels. It is trained to predict labels, and the measure is accuracy. And I think this is the most popular kind of probing, and usually when people say probing for linguistic structure, they mean exactly this kind of probing. And it sounds very simple and reasonable. You just need to train a classifier, and basically that's it. Well, not so easy. We need some sanity checks. And luckily for us, these sanity checks were already done in previous work. They are comparisons with the different kinds of random baselines. For example, we can compare representations from pre-trained model and a randomly initialized model. So what was done in the paper by Kelly Zhang and Sam Bowman. And what they did is they took a pre-trained model, trained a probe and classifier to understand how well this pre-trained model encodes some labels. And they did the same for randomly initialized model. And surprisingly, the accuracies were very close. And this is something undesirable, right? So basically accuracy is saying that a randomly initialized model not trained encodes some kind of linguistic label that are almost as well as pre-trained model. And to see differences, larger differences in accuracies of these classifiers, because we know there has to be a difference, right? These models are very different. They had to reduce the amount of probe training data. So if for our probe and classifier, we use only a small number of labels to train, the model, the probe and classifier is able to learn to predict these labels from representations which come from pre-trained model, but from random initialized model, it's harder to do so. Another type of random baselines is control tasks or random labels, which was introduced at the last year's UMNLP by John Hewitt and Percy Lane. So what they proposed is to, instead of linguistic labels, to define some kind of random labels for each word type. For example, if you have part of speech tags, for each word type, you assign a random label and you sample these random labels from an empirical distribution of tags. And again, what they found is that accuracy was not able to clearly distinguish between linguistic labels and randomly initialized random labels. So basically, accuracy said that this model encodes random labels quite well. And this is, again, kind of strange. And the authors tried to fine-tune to find a setting for a probe where this difference between accuracy for linguistic labels and random is bigger. And in the end, they end up reducing a probe model size. So they proposed to use a very small probe and classifier. And as we'll see, this is not a very good thing to do, but it is a very good way to see that current probes do not show us what we want them to show. So basically the problem is that we clearly see that differences in accuracies fail to properly reflect differences in representations. And what we want is a probe method which does not require a human to tell it what to say. And this is what we'll try to do. So now let's come to the information-theoretic point of view. First, let me give you an intuition. So once again, our main, let's come again to the first question, the initial question we want to answer. So what can we put here between representations and labels to be able to measure the relationships between these two? How can we understand that these representations actually encode these labels? And first, let me give you some intuitive examples. So here you see two examples. Dots represent data points and colors correspond to labels. And note that this example comes from the real data. If you're interested where does this example come from, you can take a look, for example, at my personal page. I have a blog post on the evolution of representations. So basically, these representations come from the final layer of machine translation encoder. And these representations on the right come from the final layer of a left or right language model. And intuitively, we can say that these representations on the left have strong regularity with respect to the labels, right? You can clearly see it. right? You don't need to put any effort to like clearly see that, yes, the figure on the left has strong regularity, the figure on the right probably not so strong. And intuitively, what we want is a method which kind of understands that these representations on the left and actually encode the labels. And the main idea, our main idea can be summarized in just 2 sentences. So here they are. Regularity in representations with respect to labels can be used to compress the data. Better compression means stronger regularity, means representations better encode labels. So now, once again, for the last time, we ask what can be put here between representations and labels to measure the relationships between these two. Now, when we remember that regularity can be used to compress the data, now we actually have the answer, right? We can put here a compression algorithm. At this point, I know most of you probably think that, oh, well, this sounds like something really strange and complicated, and problem classifiers are nice and easy, so I'm never going to use it. Please don't, please don't. It turns out that this compression algorithm can be as simple as a problem classifier. And in the rest of my talk, I'm going to try to make it clear what is this compression algorithm, how can a problem classifier be this compression algorithm, and basically all the theory behind it. And for this, I will need some help from my friends, Alice and Bob. So be ready. Adventures of Alice, Bob, and the data. Here are our heroes. Here's Alice, Bob, and the mysterious so far data. Here we assume that both Alice and Bob know representations X, but only Alice knows labels. Bob does not know them. So this labels is the data. So Bob asked Sir Alice, give me the data. But transmitting the data is a lot of work. So what can Alice do? If Alice knows information theory, it turns out that she can take a probabilistic model of data and use it to compress the whole thing. So the data is something which is huge. And what Alice can do with, so here we have our X representations and Y's labels. So by using a probabilistic model of data, Alice can compress this data and to send it to Bob easily. And so more formally, we want to compress data in an optimal way, so that we would need minimal number of bits to transmit this data. And this optimal number of bits is called minimum description length of labels known representations.
Sorry.
And so, yeah.
Can I just wanted to clarify the metaphor here? The labels are the data that is heavy, right? And so it's the model itself that is going to be a smaller representation than the label space itself, and that's what's getting transmitted.
It's not a model. We'll come to it like in just 2 slides. But
sorry.
Yeah, by using the model, we can compress these labels.
Okay.
Yes. So we are going to measure this minimum description length, and we'll call the probes which measure MDL as MDL probes. And now let's take a moment to realize what just happened. A probabilistic model of data can be used to compress the whole thing, right? And we can set this probabilistic model to be a problem classifier. And this is where the magic happens. So basically, I didn't do anything. I know this is not the best thing to say in your own talk, but I didn't do anything. I just changed a point of view, right? So we had problem classifiers before, but now by stating this probabilistic model of data to be a problem classifier, we can convert a standard probe into an MDL probe just by changing its goal from predicting labels to transmitting the data. So once again, if it's a standard, if a goal of a classifier is to predict labels, then this is a standard probe, and the measure is accuracy. But once we change a goal from predicting labels to transmitting the data, the probe becomes an MDL probe, and the measure changes naturally from accuracy to this code length, to minimum description length of labels knowing representations. And here the natural question is, why is this code length is something better than accuracy, right? But here's the thing. If you remember, what Alice is sending to Bob is some kind of mixture of data and model, right? So Alice used some model of data to compress labels. So compressed data, compressed labels is the message she wants to send to Bob. But to decode this message, Bob needs to know the specific model that Alice was using. So in some way, Alice has to send this model to Bob either explicitly or implicitly. So if the standard probe only tells you about final quality, in most cases, this is just accuracy of classifier, then their MDL probe, in addition to final quality, is also telling you how hard it is to achieve this quality, or the amount of effort needed to extract this information. And this is this is the model component. So this is the part where Alice has to somehow send the model she's used for compression. And now I'll explain you in detail how this data and the amount of effort form the total code length. And yeah, note here that by code length here, we mean the theoretical code length. So we are not going to actually send data from Alice to Bob, so we are not going to encode these labels, right? What we care about is that there exists a theoretical bound on the code length such and such. Here's what we're going to deal with. So, okay, so the total code length consists of the two parts, the data labels and something other than that, the amount of effort needed to compress the data to extract the labels. And let's start with the data part or the final quality part. Here we assume, so we care about only the data component of the code length. So here we assume that Bob already knows the model, right? So Alice, all Alice needs to do is just to compress data and send it to Bob. Nothing else, because Bob already knows the model. In this case, the optimal code length is given by the Shannon-Huffman code. It says that there exists a code to compress labels losslessly with the following code length. And this bound is optimal if the data are independent and come from this distribution pi, which is a natural assumption. Note that this is the cross-entropy loss evaluated for the model pi. And pi is the probabilistic model of data, and we want it to be a problem classifier. So basically, it's the cross-entropy of your problem classifier. This is your data code length. So if Bob already knows the model, if he has this problem classifier, the code length needed to transmit labels, it's the cross-entropy loss. So in a way, we can say that learning is compression, because the task of compressing labels is equivalent to learning a model of data, because quality of the model, cross-entropy loss, is the code length needed to transmit the data. And that's why the data component of the code length, this component corresponds to the final quality. And in a sense, this is what accuracy shows you, right? Only the final quality of the model. And I'll mention this later, but this part is also related to mutual information between representations and labels. So it's basically telling you whether representations contain this information, whether it is present or not. And that's why this part will tell you that, for example, randomly initialized model also contains information about basically anything you want to ask, because it does have this information. It's just hard to extract it. But this is something we'll see in the experiments a bit later. And a note on the term compression we use. So compression is evaluated against uniform code. So in uniform code, we assume that we know nothing about data, right? And for k classes, all classes have the same probability, and the uniform code length is the n log k bits. So if you know nothing about data, you need n log k bits to transmit labels. But if you know something, you can do better. And this is their number of bits we evaluate compression against, right? Okay, and now let's come to the most interesting part, the amount of effort. So what is this amount of effort? And again, let's start with a very intuitive example. Again, here we have two sets of representations. Again, dots represent data points and labels correspond to colors. And on the figure on the left, we see that the regularity is strong. And intuitively, if representations have strong regularity with respect to labels, this regularity can be understood with less effort. And with less effort, on the one hand, it can mean that this regularity can be explained with a very simple rule. For example, as shown on the figure, just a linear model, right? Or it can be enough to train a very small problem classifier to predict labels from representations very well, right? You don't need to use some complicated rules to explain this regularity. You can explain it simply, right? And on the other hand, if the regularity is strong, it can be revealed with only a few examples. So here you see only a few training data points, right? But it is still clear how to distinguish between classes, right? And this is exactly how this wakes of a notion of the amount of effort or strength of the regularity in the data, how it's translated into code length. And these two are just different views, different ways we can look at how strong the regularity is. And now we'll come to two compression methods which correspond to these two different ways of looking at the strength of the regularity. So a little note, so minimum description length is a theoretical thing, right? And variational and online code are different ways to estimate it in practice. Here, they are like practical ways to estimate this theoretical thing. Okay, so our first code is variational, and in this setting, a model is transmitted explicitly. So once again, I'll need some help from Alice and Bob. So here, what do we have? So we have data, labels, right? Representations, which both Alice and Bob have. So what Alice does is she trains a model of data and a problem classifier, a standard problem classifier, and uses it to compress the data. And the data here is compressed the same way we discussed before. So this code length is the cross-entropy loss, cross-entropy of the trained problem classifier. This is the data component we just looked at before. And next, what she does is she sends the model parameters weight by weight to Bob. And once Bob already knows the model, she sends compressed data. So when Bob already knows this problem classifier, knows the model which was used for compression, he can decode the message that Alice sends. And this is the general scheme of the two-part codes. So two-part means that, so basically you have a message, which is the compressed data. This is what Bob wants. And to decode this message, we also send the thing which was used for compression, in this case, model. And the total code length is sum of the two codes for model and for data. And variational code is a particular instance of these two-part codes. So please don't be scared about formulas. I don't want you to understand the formulas themselves, but rather I'm going to explain you what they mean. If you need more details, you can look at the paper. So basically what we have here is model code length, right? the number of bits needed to transmit model parameters. And here is the data code length. This is basically the cross-entropy loss. And in variational code, each weight is a random variable. It's a variational model, right? So each weight is a random variable. And once a model is trained, the number of bits needed to transmit all the parameters is the divergence between learned parameters beta and prior parameters alpha. And to give you a very intuitive explanation of how variational code actually compresses the model, let's why can't we just transmit model parameters explicitly? So we have a model, we have some number of weights, and why don't we just transmit these weights explicitly to both? Well, because deep learning models have a lot of parameters, and even if this is a problem classifier, if you're going to transmit each parameter, like using, for example, I don't know, 8 bits for each parameter, like each parameter is a number, you're gonna spend like 8 bits, for example, for each parameter, it's gonna be inefficient. And how variational code is a good, a smart way to go about this is that once a model is trained, the weights which have high variance can be transmitted with lower precision. So what is a variational model? In variational model, each parameter is a probability distribution, right? And each time you apply this model, you like sample each weight from the corresponding probability distribution. And when a model is trained, if some weight has high variance, it means that the value of this parameter is not important for model. So basically, if some parameter after training has high variance, it means that each time you apply a model, this parameter can have very different values, and the model basically doesn't care about it. So why should we care if the model doesn't, right? So the parameters which have high variance, we can transmit them using like very low precision. Basically, we can just send some kind of default value instead, and we do not need high precision to transmit this value. And this is how variational code can transmit model parameters efficiently. Because most of the parameters, as we will see, most of the parameters can be transmitted with only a few bits. And
is there any independence assumption of the parameters in that argument?
Independence, when you sample, yes, if you mean that when we are sampling each weight from the corresponding distribution, yes, usually there is.
I mean that the parameters of a model may be correlated, in fact, and so there could be high variance, but the interdependent variance is low.
No, so your parameters are independent. So the probability distributions corresponding to the parameters are independent. So when you're sampling, you're gonna have like uncorrelated things. So basically what you're saying, you can have like parameters with high variance, but it can be important for some other parameter. This is not something that can happen, no.
Okay.
Okay, so and what is also interesting about variational approaches, that the specific method we use, Bayesian compression, will allow us to also look at their model architecture. So not just their model size in terms of code length, but also at their architecture. As you probably know, people interested in variational learning, they have a lot of fun with different priors on these parameters. So depending on priors, you can get a very different properties of your model. So there are some works which show that by setting their priors in the right way, we can get the model like with induced sparse architecture. So this is something you can see on the figure. So what we'll end up with the probe classifier is a lot of pruned neurons. So in the end, we'll have like two ways of assessing this model component of the code length. The code length itself, the calibrations term, right? It's the number of bits needed to transmit the parameters, and the architecture itself. And what do we expect to see with the variational code? So intuitively, if the regularity is strong, it can be explained with a simple rule. It means that we'll have a small probing model. A small probing model means easy to communicate. So only a few parameters require high precision. And this is how it can look like, something like, ideally, something like a linear model. And note that we'll get this variational code gives us model size as a byproduct of training. So we won't have to like manually tune probe hyperparameters. We won't have to, I don't know, to perform exhaustive search over model architectures as done in Hewitt and Lane in control tasks paper. We get this as a byproduct of training. So basically we run a model and it says, okay, for this type of representations and labels, I have this kind of model. For that ones, I have another kind of model. And this is something we will get for free. Okay, now let's look at the other compression method, online code. And online code is a very interesting one because it provides a way to transmit data without transmitting model explicitly. So it's kind of an implicit way to transmit the data. In this setting, Alice and Bob agree on the form of the model, random seeds. Basically, they agree on the whole training pipeline. So basically, they sit and say, okay, how will we train our problem classifiers? We'll have such and such architecture, such and such initialization. We'll train for such and such epochs, for the such and such learning rate, and so on and so forth. And also they choose time steps at which they split the data set into portions. And then Alice sends data by portions. So first, so here is our data, right, split by portions. First, she sends the first portion to Bob without compression. Without compression, using uniform code. Remember, n log k bits, without any compression because they don't have any kind of model yet. And now when both Alice and Bob have this portion of data, they can use it to train a problem classifier. And since they agreed on the training pipeline, they can do it and to get the same, exactly the same model, right? So, and now Alice uses this model to compress the second portion. And the trick is that she can send this compressed data to Bob without sending the model, because Bob already has exactly the same model. And this is the trick. So now Alice can use the model she has to compress the next portion. And Bob can decode this next portion because he also has the same model. On the next step, they already, both Alice and Bob have two portions of data. Remember, Bob already received the second one, and they use all this data to train the next problem classifier, the next model. And again, Alice can use this new model to compress the next portion of data. And this happens until the whole data set is transmitted. So this is a way Alice can send all the data without sending the model. And the total code length is sum of all the sent portions. So first we have this portion 1 compressed with the uniform code without compression, right? And then we have code length for the portion, for the next portion compressed with the model trained on all the previous portions, right? So the model I trained on all previous portions is used to compress the next portion. And this is the cross entropy. So this is the data code length we looked at before. And this is this is a neat way to transmit all the data without transmitting model, but what if we still want to look at the model complexity or this amount of effort, right? So because in variational code, we had explicitly this data component and model component. And we could say, okay, this model component is large, the amount of effort is large, or it's small and the amount of effort is small. But in the online code, we don't have this model component explicitly, right? But we still can like extract this model component from the total code length. How can we do this? So online code length, the total code length, is the number of bits needed to transmit the data if Bob does not know a model. So if Bob does not know the model, we'll need to use this number of bits online code length. But if Bob already knows the model, we only need this like cross-entropy loss, like yes, so the data component. So what we do is to get the amount of effort component in online code, we subtract data component from the total code length. So here's the data component, and the difference between online code and the data code is this model component for online code, or this amount of effort component, right? And again, a bit of intuition. So what do we expect to see with the online code? So if the regularity is strong, it can be revealed with only a few examples. It means that somewhere earlier, so Alice sends data by portions, right? And somewhere early in this transmission process, the models are going to be already very good, right? So the compression is going to be very good somewhere early in this transmission process. It means that the total code length will be small. And note also that online code length is related to area on the learning curve. And a bit later, I'll show you the code length and learning curve, so it will be clear. Okay, finally, a small comment. So let us remember what previous work had to do to see larger differences with either random model or random labels. So it had to either reduce the probe model size or to reduce the amount of probe training data. But reducing a model size is in a way an attempt to indirectly manually force the standard probe classifier to account for this amount of effort component of variational code. Because so what's happening here? We train problem classifiers. We don't see differences in accuracies, but we want to see differences in accuracies. So what Hewitt and Lane did, they suggested to reduce probe model size. So they forced problem classifiers to be very small to see differences in accuracies, right? And this is kind of an attempt to indirectly account for this amount of effort component in variational code. On the other hand, reducing the amount of probe training data, which was done in the other work, is also an attempt to indirectly manually account for this amount of effort component in online code. So we are not seeing large differences in accuracies. So what we do, we'll try to not give a large amount of data to our problem classifiers. And note that these were more like observations. So if we reduce a probe model size, we will see more reasonable differences in accuracies. If we reduce the amount of probe training data, we will see more reasonable differences in accuracies. But with MDL, with minimum description length, MDL has this amount of effort component directly in a theoretically justified way. And depending on the specific method used to evaluate MDL in practice, this amount of effort can either show how hard it is to learn using smaller models, like in variational code, or how hard it is to learn using smaller data sets, like in online code. So this is all kind of related to previous work in a way that the previous attempt to somehow see more reasonable behavior of problem classifiers, they basically, in a sense, that they indirectly also tried to account for this amount of effort. Okay, finally, let's come to the experiments. So in the paper, we have two parts. When we look at the both types of random baselines. In the talk, I'll mention only one, this MDL and random labels. If you want the other one, you can look at the paper. So MDL and random labels or control tasks. First, let us recall what a control task is. So each word type is assigned to random labels. And these labels are sampled from the empirical distribution of tags, and they are fixed and do not depend on context. So if we say that the word cat is a verb, then it's going to be verb in any context we see, right? So intuitively, control tasks measure the ability to remember from word type, okay? And so what we are going to see, first we'll see that the two compression methods, variational and online code, agree in the results. And this is a good thing because, as I mentioned MDL is a theoretical thing, and variational and online code are ways to estimate this in practice. And if they agree in the results, it means that the estimate is good, right? Next, we will see that MDL identifies control task easily while accuracy does not. Then we'll look at the amount of effort component, the most interesting part, which is new in MDL, right? And we'll see that the amount of effort is small for linguistic task and large for control. So it's easy to extract part of speech tags, but it's really hard to extract random labels. And this is kind of what we expected to see. And finally, we'll look at the stability of the results in hyperparameters and random seeds. Okay, here are the results. We follow the setup from the control tasks paper. So here, this is the ELMA model. Layer 0 is the embeddings layer. The results are shown in pairs for linguistic and control tasks. Yeah, so, and we show accuracy. So here's accuracy. The first number is for linguistic tasks. The second one is for control. And the code lengths for the two compression methods. Okay, so first we see that the two compression methods agree in the results. We see, for example, that the best layer is the first because it has the smallest code length. So the minimum code length needed to transmit the data. And also we see the large difference between layer 0 and contextualized representations. And this is really great because with accuracy, it's not so clear that the difference is huge, right? And here it's like almost twice of large. So it's really hard to extract something from the embeddings. Next, we see that for control tasks, scores becomes larger as they move up, which is expected because control tasks measure the ability to remember from word type, right? So the farther away we are from word type, the harder it is to predict this fixed random labels. And finally, we see that code lengths for control tasks, so the right number in each experiment, the code lengths for control tasks are substantially larger than for linguistic. It means that we clearly see that it is harder to predict random labels compared to linguistic labels. And what is especially interesting is layer 0. So if we look at the layer 0, we'll see that accuracy basically says that for control task, accuracy is higher. So basically what accuracy is saying is that it is easier to predict random labels than linguistic ones. And in this case, this is kind of reasonable because because part of speech tags can be different. So for the same word type, part of speech tags can be different depending on context, and the model cannot predict that based on the embeddings only, right, without context. But for control tasks, each word type has only one label. So, but if we are asking do these representations encode some kind of labels, accuracy basically is saying that representations encode random labels better than linguistic. And this is crazy. This is crazy. This is not what we want to happen, right? And luckily, MDL says that random labels are at least like almost twice worse than the linguistic ones. And why is this happening? Because code length also, in addition to final quality, it has this amount of effort component. And now let's look at this data and model components of the code length. So here we have the code length for each layer, for the two tasks, base, this linguistic and control, and for the two compression methods, variational and align code. And first we see that for control task, their model component, the orange one, is very big. So basically, the amount of effort needed to extract to predict random representation, random labels on representations is very large. And this is what's kind of cool about this MDL, because if we now come again to this layer 0, we'll see that yes, what we see is that yes, the data code length is smaller for control task. This green component, see that this green component is smaller, and this is basically the accuracy of final quality. So it says that embeddings contain representations, contain information about labels. Yes, and if we want to predict this, the quality will be higher. Again, because for each word type, control tasks have the same label and part of speech text can be different depending on context, right? So it's expected that quality is higher for control tasks. But the amount of effort or model component is very big. And this is, yeah, and according to this, the total code lengths, their random labels are worse than the linguistic ones. So, and this is what is cool about MDL. So it does say, yes, you can predict random labels, you can, and you can predict them with higher accuracy, but you need a lot of effort to predict these labels. And this is what kind of cool, because here we see that the amount of effort is small. So embeddings do encode linguistic tags, part of speech tags. It's really easy to extract part of speech tags from a trained model, right? But it's very hard to extract random labels. And now, if we look, so here are the learning curves. This is not what I wanted to show you. Here, if we look at the pruned architecture for variational probe, remember I promised you that we will be able to look at their pruned model architecture. So we are starting training from this kind of standard setup, and in the end we get pruned probe architecture. This is like an additional interpretation. And what we see is that for linguistic task, final probes are very small. For 45 labels, we have like 33, 17 neurons at layers 2, 3. This is a very small problem classifier compared to the starting one, right? But for control task, the model architecture is quite dense. And again, so we got, note that we got this probe architecture as a byproduct of training. We didn't have to like manually tune this model size like in huge layer, right? So we have this variational probe, and it's saying, yes, I can predict linguistic labels, and it's enough for me to have a very small probing model, because I don't need to put much effort into extracting this linguistic labels from representations. But I also can predict random labels. But to predict random labels, sorry, I will have to have larger problem classifier, because I need model capacity to do that. And this is what I like about MDL, and I think this is what we really want from our problem methods. Yeah, once again, we got this as a byproduct of training without manual search for hyperparameters. Okay, finally, let's look at the stability of the results. Here are different settings for problem classifiers. For example, we can train one layer MLP as a problem classifier. We can train a 2-layer MLP as a problem classifier. We can have like 50 or 1,000 neurons in this probes, right? And depending on this setting, on the probe setting, we can have different results. So accuracy, these are all the settings from the Hewitt and Lane paper. So here we see that for 8 settings out of 10, accuracy says that the control task is better. And we already discussed this. This is crazy. The model cannot possibly encode random labels better than linguistic. And only in 2 settings, it actually says that the linguistic task is better. But for MDL, for all the settings, it says that the linguistic task is better and the results are stable. So with MDL, you don't have to tune this probe settings. You don't need to wonder like, which number of neurons do I have to put in my problem classifier, which number of layers, how this is going to affect my results. It's not going to affect your results because MDL is reasonable. And what is interesting that with the standard problem, results also can change even depending on random seeds. For example, here I've run the same setting, the same model with different random seeds, and I got different results. And actually, this experiment was kind of it was an accident because I first trained like with random seed 0. I got different results from the paper, from the control tasks paper, and I had to run with other seeds to get some kind of similar results. And this is what happens with the standard problem. And even if you are willing to like train your problem classifier, I don't know, 10 times and to see like, okay, which is the most frequent result, it's still the scores are very close and it's really hard to make any conclusions. For example, here it's really hard to say which layer is really better at encoding some labels. But with MDL, for all random seeds, so the results are stable and the scores are well separated. So here we clearly see that the code length for layer 1 is smaller. That is why ALMA encodes part of speech tags are better at layer 1 than at all the other layers. Okay, for more experiments, you can look at the paper, and I think that's it. So we propose MDL probing that characterizes not only probe quality, but also the amount of effort needed to achieve it. It's easy to measure on top of standard probe training pipelines. So you're still training probing classifiers. You just do different things with them. And it's more informative and stable than the standard probes. And to give you some kind of intuition of the amount of effort, so what is the difference between whether representations contain information and this amount of effort? For example, let's try to recall what we had for breakfast today. I still can recall that. I'm sure you can too. I hope you all had breakfast. It's still too early. I know it's morning where you are, but and now let's try to recall what we had for breakfast this day 10 years ago. I can't remember that. Well, maybe I have this information somewhere. It was me who had this breakfast 10 years ago. And so I have this information somewhere encoded, right? But it's really hard to extract it, right? I don't need to put much effort to remember what I had for breakfast today, but I do need to spend a lot of effort to at least try to recall what I had for breakfast like 10 years ago this day. And this is the difference. And this is what the standard probing cannot tell you. It only tells you whether the presentations contain this information or not. But MDL also tells you this amount of effort or how easy it is to extract this information. And if you want to remember only a couple of sentences from today's talk, let it be these ones. So regularity can be used to compress the data. Better compression means stronger regularity, means representations, better encode labels. And for more details, you can look at the blog post. And there's also some some other stuff I have, but yeah, let's just say, yeah, let's just say thank you.
Thank you so much, Lena, for the great talk. So I will start with a question that came up in the chat. Is there some understandable relationship between HTTP's notion of relevant information and MDL?
Between the relative information, so there is a relationship between the data component of the code length and mutual information. So basically, the data component is related to mutual information, and there was the other paper at ACL basically arguing that you shouldn't follow Hewitt and Leon in choosing small problem classifiers, because you do need to have this a good estimate of mutual information, and to get a good estimate of mutual information, which is accuracy, you still you need to have like high capacity problem classifiers. So this accuracy or the data component of the code length is related to mutual information. But mutual information is only part of this total code length, because we also need to know this amount of effort, how hard it is to extract the information. So one part says, well, the information is there. The other part says if this, how hard it is to extract it.
Are there, okay, another question, sort of similar question. Is there some relationship between the representation selected by MDL and that selected by mutual information, such as minimal sufficient statistics?
I'm not sure what you mean by representations extracted. It's not representations extracted. It's code length, right? It's relationships. Yeah, and I think I've just answered that. So yeah, so mutual information, it's only part of the code length. So the data part of the code length is related to mutual information. And MDL is different from mutual information in the way that it also tells you not only whether the information is there, but also how hard it is to extract it.
Are there any other questions from the audience? If not, I'm gonna ask one.
I have a question, if possible. So this approach evaluates the quality of a model by sort of looking at what these layers actually encode relative to a label space. I was wondering, what you would really want is to use that to guide the learning towards a representation that has smaller description length. So do you see,
True.
is this applicable
True.
sort of more directly, as opposed to just run multiple times and then just pick the model that has the minimal description length, but to actually sort of use this in the learning cycle more immediately?
Yes, in a way, variational learning, it's what variational learning does, because variational learning in general, it's related to this, it can be interpreted as optimizing minimum description length, because it has this data component cross entropy loss, right? And it also has the scale divergence, which can be interpreted as the code length needed to transmit model parameters. But variational learning people usually have different kinds of weights through this part of the loss functions. But if like both weights are ones, it's exactly MDL. So what you're optimizing is MDL. And this is kind of the trade-off between complexity of the model and quality. And yes, you can do that. And I think at last year's Human OP, there was a paper also using information theory to get this small representations which encode something. They did it through information bottleneck. I think it was the best paper wrote. So they basically applied information bottleneck to learn small representations, to compress representations according to this one. I think MDL can be potentially used to do that too, yeah.
Thank you.
So do we have any other questions from the audience?
So I think I have a question. So I think maybe my previous question is confusing. So my question is like, so suppose that we applied the MDL probe on top of some different layers of a model, and some layers has some smaller code length, some layer has a larger code length. So what this code length tell us about the representations of the layers? So is that true that the representations of the layers with smaller code lengths is more related with the minimal sufficient statistics or the information bottleneck, or it tells us that the my question is what the smaller code length tells us about different layers?
It's a good question. So intuitively, just let me show the figure. So intuitively, smaller code length means a stronger regularity. Stronger regularity means that it looks kind of like, sorry, it's gonna take a while. So stronger regularity means something like this. So this one, what you're saying about information bottleneck and sufficient statistic, yes, I think in a way you can say that it's related to information bottleneck, because what information bottleneck is saying that as you go, if you're talking about deep learning, right? If we go from bottom to top, the information which is irrelevant to the task is being, so the representations forget information which is irrelevant to output and retains only information which is relevant. So if we have this smaller code length, it means that this information is relevant for the task, and maybe it could say us something about which kinds of linguistic phenomena are more, from the model's point of view, which types of linguistic phenomena are more important for the tasks it's trained on.
Okay, thank you.
Any other questions from the audience? Okay, great. I also have a question that I think was in part answered during the other question. I also have a one-on-one with you, so I'll keep it for that. So not to bother you twice, but thank you for a great talk. And I think this is a good time to give Lena a break before the one-on-ones. Thank you everyone also who joined us, and I hope to see you all again soon.
Thank you. Bye.
Thank you. So I have to disconnect now and to join the other meeting, right?
Yes, the one-on-ones.
Okay.
Great. Thank you so much again.
Thank you. Thank you.